Push-ups, Phil? Yeah.
Are we going to talk about your rant, your email rant?
I wouldn't call it a rant.
And your email?
Yes, we'll certainly talk about the email.
Okay. There's a problem.
I'm sure some more people will trickle in. So it's looking at small bodies and asteroids. We'll probably get through comets as well. We'll try to talk about how collisions have shaped our solar system. And then we'll talk about how solar systems form. And then immediately after we talk about how the solar system formed, we'll talk about why we're kind of unusual in the universe. We'll look at planets outside of our solar system and show us what we can learn about those things. And so right about here, as I mentioned before, we're going to start running out of content. I can do what I want to do, but if you have a particular interest, I'm going to ask you to write down 5 things that you want to learn about, and then I'll look at all of them and I'll see where the most correlation is, and you'll have little bonus lectures, material that will not be on the final exam. So I give you more opportunity to study for the final exam, to do anything else you want in your life, just for fun. Is that okay? Okay. Okay, so there's also, as mentioned previously, there's gonna be observatory open house on the 7th, or sorry, is that correct? Yeah, the 7th, so the day before Tuesday, on Monday. Is that correct? Maybe, something like that. Yeah, so on Monday, and then we'll have another one on the 15th, but that will be, wait, did I do this right? 7th, yeah, 28th will be the other Monday one. And I think this one is on the 17th, not the 15th. So we have our normal one on the Thursday, hopefully after they replace the domes. So we'll see brand new telescopes unless they take longer than they're supposed to, which I'm worried about that happening. And then we'll have another one on the 28th. And then we'll have one here during finals week on the Thursday. That's 4 more opportunities if you haven't done it already. If you've done 2 already, just remember to send those in. I do have a record of your names, but I just need the write-ups. Okay. Oh. Yeah, if you have pictures, that's better. Okay. So for today's class, oops, hold on. Let's move around here. As I mentioned, we're going to talk about asteroids and comets, but unfortunately, we have to talk about one thing first. Okay, that's my email from yesterday. So to clarify, I'm not necessarily talking to everyone in the room, but I am talking to a significant fraction of you. Okay. So what does it mean? Okay, it's this idea of academic dishonesty. Okay, you use something like Chegg, Quizlet, Google, or another resource to answer your homework question. For example, you could go into the book, you could copy and paste from the book, and you could put it into the master. Right? Is that academic honesty? No. That is plagiarism. Because you did not cite where your work came from. Is plagiarism acceptable? No. Okay, so if you didn't know that, right, this is when you would come up to me, you'd be like at the end of class, right? You'd say, I'm sorry, I didn't understand, blah, blah, blah. There are 2 students who I found this rampant in. Okay. There's 7 people who I noticed this in multiple homeworks. 10 people I only noticed in 1 homework so far. And 3 people have already come forward to take responsibility. Okay. So what happens? What does taking responsibility look like? You talk to me. That's the first part. Okay. I gave a time period in that email. Some people came to me right away. They said, listen, let's talk. And I was like, good. They told me which homeworks where the aids were used inappropriately. I removed them from the person's grade. Okay. And we're going to treat that like a learning experience. Had no idea, fresh in school, right? However, if I see the second part, or you don't come forward, then we have to do B. Okay. So you might be saying to yourself, this class is a pushover. I don't give a fuck. Like, I'm just going to do what I've been doing. And then I have no recourses, right? So that's this. Okay. This is not what I want to do. I would rather resolve this amicably. So if you don't come forward by Friday when I ask you to, you admit only to some, but not all of the homework, so that I cannot remove it from your grade. Or if I see you say, okay, well, I'm going to admit to the ones that he's caught, but I'm not going to admit to anything else, or I'm going to keep doing it in the future, then how can I give you a grade? Right? How can the grade that I give you reflect your learning? That's my responsibility as a professor. I don't just stand here. I mean, I do stand up here because I like the sound of my voice. But my job to the dean of the school, the dean of the natural sciences, is to say that when I give you your grade, it's meaningful. And if the work that you're doing is not your own work, it can't possibly be meaningful, right? Okay. All right. So these are the actions that they could potentially take. I don't make any choices about that. Probably this, if you get reported, it's probably immediately these 2. I don't know about that one. Okay. Question? Yeah.
So you want us to list the site of the source when we're doing the homework? If we need help with it and we find it in the book, is that what you want us to do?
So if you use the book, that's fine. I said very specifically, you can't use websites like Chegg, that you can't use things like Quizlet, that you can't copy and paste answers from somewhere else. If you take something, for example, you're like, I went on Wikipedia and I looked up tectonics and I put it in my own words, perfect. That's exactly what you should be doing, right? I have no problem with you learning from other places. Putting it into your own words is called paraphrasing, right? Obviously, the definition of the word tectonic, if I ask you to write it down, it's not going to be perfect, right? You put every single word exactly how it is in the Wikipedia article, that doesn't demonstrate to me that you understand it. That demonstrates to me that you know how to copy and paste. Guess what? Every person with a computer knows how to copy and paste, right? So I want to see your understanding come through. And there's a lot of ways that I've been trying to do this. I can see it in the lecture tutorials when you answer those questions. I can see it in the exams, and I can compare all three of these sources. Guess which one stands out the most? Master and home. Okay. Same quality of the answers is not consistent, which is what initially drew my attention to this. Okay, so I see really, really interesting, perfect explanations in the master. Not for everyone, for some people. And then this another person is the same exact answer. Exact. Those are the two people that I mentioned at the beginning. These two people. Okay. Questions? Hey, kind of a bummer, right? It was not a fun Halloween for me. So let's try and move forward. As I mentioned here, when you come forward, do not come forward in class. Email me and send me a Slack message. We can talk in my office hours. You can make an appointment to talk to me after class. I will go after class to my office. But don't come forward right now. Don't raise your hand. You're like, I'm sorry, I did it. It's not what I want to have happen. Okay.
You can't use one of those, but you have to use your own words.
What do you mean? You want to use one of these?
You have to use your own words.
You have to use your own words, yeah. So if you're using Chegg as a study guide, I mean, it's your money, you're allowed to do whatever you want. Okay, I don't recommend it.
In your own.
In fact, I noticed that people, there's a discrepancy. You look at the difference in the test score versus the homework score, and you sort them with color, they pop out. Okay, lots of ways. You saw that how much I care about data. Saw how I wrote all of those stupid things about the exam. I typed everything in. I'm a dork. I'm a nerd. Okay, I figured this stuff out. It's really obvious to me. Seems sly and subtle. Promise it's not. Okay. All right. Let's talk about cool things. I got a brand new clicker. Everyone likes that. Oh shit. Did not plan that, but that was cool. Okay, so what's this? Is that a comet? Is that a yes? No, no. What was that? Yes, I was driving home on Thursday and I saw this. It's the most beautiful thing you can see in the world is a launch, in my opinion. Okay, so what do you see here? This is the launch from Vandenberg, and as it's going out, it's pushing out gas to make it go fast. It's being left in the sky, like a contrail. Okay. And so this is the picture I got while driving. Don't tell anyone. So that's the first one. I got this picture and it's really cool. I don't think you'll be able to see here, but you can definitely see it in the posted slides. So this section here, they're like different, like when it's emitting or like putting the gas out the bottom. So this is the first stage. There's 3 stages in the launch, and then it stops firing for a little while. It's just floating through space, and it stops firing. You can see that, and this is when it starts firing again. And there's a whole second stage, and then there's a third stage. And you don't get to this picture here where you see this really cool, like whatever that is. You can kind of see the 3 stages: the first stage, second stage, third stage. Right. So that was the first part that I caught. And then I forgot, and I was like driving, it was like behind me. I was like, I try not to do that. And so then I did this one afterwards. This is called a noctilucent cloud. So you can really only see them right after the sun has gone down. And because they're super high, they are still illuminated, but we are not. So you get this beautiful contrast between, over here, no illuminated light, and then it's bouncing off of this, which is just the smoke from the exhaust. Kind of fun, right? Yeah.
I think I took the picture of the same thing.
Yeah. Yeah, it's pretty cool. I mean, if you've never seen a launch, even to just go up to Vandenberg, this is something I realize I have to do now. I'm gonna have to like keep a little, because they have like a website where they update all the sunset launches. Sunset launches are the best. Night launches are second best. Day launches, boo. No, I'm just kidding. Okay, so what are we gonna talk about? Is that a comment? What does it look like? An asteroid. Why did you know it was an asteroid?
Doesn't a comet have, well, an asteroid just looks like a solid rock. When a comet maybe has light and it's going a little bit faster.
Okay, okay. I like the first part of that. I'm not sure that I understand the second part. What do you mean by?
Like when you see a comet, it's like I've seen a comet before and it enters the Earth's atmosphere and then like it goes out. Like it's quick.
Okay, so you're thinking of like a shooting star.
Yeah, kind of.
Okay, so shooting star, comet, and asteroid. We're gonna learn the difference today. Shooting star is another word for that is meteor. And they're actually not comets. Comets are more rare, and they usually last like all night long and even for weeks. So you're right that this is not a comet. This surface is rocky or icy. How can you tell it's rocky?
See it's a light rock.
What? Because it looks like rock. That's a good answer. Don't see any light. Like you can kind of like get that feel, when you see something and you know what it would taste like. You've ever done that? The texture. I don't know how your brain knows this, but you can kind of look at the texture and you're like, that's a rock. Right? Another way of thinking about this is it doesn't look granular. Like think about snow, right? Have people seen snow? Okay. It's like sharp. It's not perfect, right? Okay. So this is a rock. So this is not a comet. Good. What kind of things do we see on it? Craters. Good. What else? What was that? Smooth areas. Where do you see smooth areas? Curvies. Oh yeah, so there's like these big old smooth indentation. Yeah, I like that. That could be like a maybe old crater. So is that erosion? We expect this thing to have an atmosphere. Why not? Exactly. So how can you tell it's too small? Not just already know. What about this picture tells you it's too small? Yeah. It's not circular, right? So the fact that it's not circular tells you that it's small. Because if it was big, why would the big circular? Gravity do smoosh. Okay, gravity do smoosh. Good. Okay. So we know it's not big. So it's not big. Is there volcanism here? No, unlikely to be volcanism. If there's no volcanism and it's small, then the likelihood of erosion is very much. Okay. People work through that. And we're going to brush those skills off again. Okay. All right. So what's an asteroid? Asteroid is just junk. Space junk, like OG space junk, not like old spacecraft. Okay. When I say OG, I mean really OG. So this is the leftover debris from when the solar system itself was formed. Okay. So if you look at the orbits, the place that we think of this asteroid belt is in between the orbit of Mars and the orbit of Jupiter. Okay. And you see that there's the sun, and then you know how to name the order. What's the interior one? Closest one. No, interior. What's this planet called? The sun, and then Mercury, and then Venus, and then Earth, and then Mars. Okay. And then there's a space, the big old gap. and that's the asteroid belt. So in this gap lives a bunch of junk. And that junk could have been a planet, but Jupiter was like, And it basically broke this piece and made it into this beautiful thing called the asteroid belt that you can't see with your eye. Very dark and dirty. Okay. Okay. So Jupiter's gravity likely prevented a planet from forming there. And in fact, as we'll see a little bit later, it's going to have a lot of the same behavior that we've seen from the rings, say the ring structure in Saturn. We saw, for example, in the ring structure in Saturn was not uniform. So even though this picture, really well drawn picture, right? They look like they're uniform, they're not going to be uniform. And we'll show you that in a few seconds. Questions about this? Okay. So here's the regular sizes. Here's the Earth. I guess we haven't done this in a long time. That's the Earth and that's the Moon to scale. Is that surprising to people? You tend to think of the Moon as like a lot bigger. Or at least I look up in the sky and think of it as like a comparable size to the Earth, but it's not. It's real small. This is Ceres. So this is the order they were found. They get this fun designation. They're one and then the name of the thing. And so as we find more and more and more, that number gets bigger and bigger and bigger. And there's a conference every 3 years. I don't know, I did that. 3 years. Where like people who study asteroids get together. And the biggest honor you can get is that they will at dinner just name an asteroid after you. That's like what I'm trying to go for. They have another meeting, this name, trying to get there, get up at dinner, get an asteroid. They're small, they're like chunks of nothing, so it doesn't really matter. So here's Ceres, here's Pallas, there's Juno and Vesta. Not very big, but Ceres is round or non-round?
Round.
It's round, yeah, right? What about Juno? Yeah, it's kind of hard to tell. Probably not. Vesta? Yeah, kind of hard to tell. Okay. So these 4 objects comprise 2/3 of all the mass. So there's not a lot of big things. It's mostly really small stuff. Okay. Is there any reason why someone on Earth would care about what's in the asteroid belt? Other than if you've seen The Expanse? Okay, we'll get to that probably Thursday. We'll talk about why this is a potential issue. Okay. So there's the relative sizes again, and let's keep going in the numbers. So there's Ceres, Vesta, and then some other stuff that we're going to talk about. The Moon, of course, being the largest object here, and so there's the different shapes. Vesta was circular, and the rest of these rapidly become non-circular. Okay, so this one here, 25-143. These are all named after people. Not me though, unfortunately. You can't even see it there. Like I didn't, even in the picture that I created, you can see it. You can kind of see that one. And the scale here is 500 kilometers. So stuff that's about smaller than 500 kilometers really is not circular. Yeah.
How do they become uncircular?
How do they become uncircular? Okay. Let's work backwards from that question. Do we think they are all originally circular? Or do we think they're whatever shape rock is? Whatever shape rock is. How do they become circular? So they have to become large enough that gravity can pull them together. So what is it trying to do? All right, so currently, this, I don't weigh enough, hopefully. So if I sit on this, I don't go through this. Why? Yeah, but rocks are solid, like that's solid too. What are the 2 things that are balancing here? So I'm being pulled down by the Earth, and this has a structural integrity, right? That's strong enough. If I tried to do it on this, right, it would fall through the piece of paper. Paper can't hold me up with nothing underneath it. Okay, so eventually, the force of gravity is so strong that the rocks fail. they break, they crumble. Okay? And they crumble so that they are mostly smooth all the way around. Smooth. It's circular. Right? Because if there's a piece that's sticking out here, then it's being pulled towards the middle and it crushes the rock. Pushes the rock out. Okay? And if you're interested in why it's spherical, we can do well, we won't do it. I'll show you a derivation for why the force of gravity is basically treated like a concentration. If you have a sphere, it's concentrated at the middle. It uses integrals, but it's fun. You like integrals? No, no one likes integrals. Okay, no, we won't do that then. All right, so let's look at these ones here. We're gonna make this one big now. And we're just gonna look at how weird these things are. They have fun names, like Dactyl. I don't know why I like that name. Anne Frank, famous name. Eros, name of a god. Then over here, I drew this line in because this stuff on the left is are asteroids, and this stuff on the right are not asteroids. They have a different naming convention. You know what the stuff on the right is? Bottom. Comets, very good. Yeah, right. We talked about asteroids and comets, asteroids and comets. What's the major difference you see between the populations? Yeah, a lot bigger, right? So every stuff, all the stuff here on the left is big, and all that stuff in the bottom is small. And that's certainly correct, right? There's no massive comets, or at least not enough. We'll talk about why that is. So let's look at their geology again for a couple seconds here. What kind of repeated stuff do we see? Craters. You see any smooth objects, like no craters on the surface. On the ones that have the resolution that we can see the surface with, aren't like dots. No, I don't see any. Right? This one's got a bunch of craters. This one's got a bunch of craters. These one have craters. These all have craters. Okay. Anything else we see? What's that? Lines. That's correct. Lines. We would also call those. What's that? Streaks. Okay, so streaks would be like if it was from the surface out. This is a different morphology. If I saw these lines on Venus, I would call them tectonics. So this is a weird version of tectonics, where these are probably compression marks. So this thing has either been compressed or rarefied, expanded. And so these lines are along the direction of the compression or the expansion. Okay? So there's tectonics here, weirdly enough. Not the tectonics you think of, we're not thinking plates. These things are probably don't have a core in the middle and then stuff outside of that crust. It's probably just rubble all the way through that's been swished. Okay. And then this stuff on the right-hand side, these are comets. We'll have a zoom in on them in a little while. This is 1P Halley, the big one. Have you ever heard like Halley's Comet? It's really beautiful. And Halley's Comet creates a lot of shooting stars, which are incorrectly named. But that's because it's putting off a lot of stuff, as we'll see in a little bit. So keep in mind these relative sizes. We'll come back to this in a little bit. Okay.
So the tectonics, they get squashed, is that what it is?
Yeah, so this version of tectonics here is a different version of tectonics than what we've seen on a planetary body. Right? Yeah, probably compression here. And this can tell you a little bit about the history. We'll look at it when we look at a comet later. Got to use them. Okay, I'm gonna show. There was a place for a joke and I missed it. I'll show you that when we get to comets. This will be Ceres. So this is a video of Ceres. This is the largest one. And this one looks circular, non-circular. Very circular. So bigger than 500 kilometers. Anything else that's weird?
There's like a bright light.
Yeah, looks like there's like a light tower or something. Anyone have an idea what that might be? Ice, yeah, so typically when we see reflective material, our brains just think white, and then in space, it's not like someone's blanket, it's ice. And that's exactly what it is. This is ice trapped under the surface. It's being shown to the sun. That heats it up and helps it to get more ice off the surface, evaporation. Okay. This one here is chock full of impact craters. This one really doesn't have as many tectonic features as we've seen before. So that either speaks to the fact this is extremely old. The exterior cooled, found its shape, totally cool, and then was smashed a bunch. As opposed to smaller asteroids, which maybe are like this or weird and crumply, and they get hit and they break off a piece, right? And then you have two pieces and they start to crunch back together. That might not make sense, but we'll get to more of this in a little bit. Okay. So as I mentioned before, most asteroids live in the asteroid belt between Mars and Jupiter. So there's Jupiter, there's Mars. This is a representation of all the asteroids that we know about. So every dot there is a real asteroid, not to scale, obviously. As we saw, most of the mass is in 4 objects. And then Jupiter has some fun ones. Trojan asteroids, has anyone ever heard of those? These are asteroids that basically flank Jupiter. So as Jupiter goes around the sun, let's say I'm Jupiter and you're all the sun. So it goes like this around the sun. You'll have asteroids in front and behind that have exactly the same period. They go around the sun at exactly the same rate as Jupiter does. And then they're a totally different body. They live in this little thing out there. If I take that same picture, right? I grab every single object, and I grab the average distance it spends away from the sun. I'm going to call that A, average distance spent away from the sun. Okay, now I'm going to plot it. Okay. Or I guess I'm doing, that's on the top here, average distance, and the orbital period, those are related. And this is the number of asteroids. And there's Jupiter's location. It's about 12 years for Jupiter to go around the sun. There's the Earth. It takes 1 year. There's Mars. That's the edge of the asteroid belt. And that's the distribution. Did anyone think, okay, we should expect uniform between here? You're surprised maybe? There's these gaps. Yeah, it might be surprising. I was definitely surprised when I first saw this. But these gaps are basically created in the same way as the gaps that are created in the rings. You have an object that has a bunch of mass being pulled by Jupiter, right? So Saturn and its moons were interacting. They're creating holes or gaps in the rings, and that's the same thing that's happening here. Okay. We talked about orbital resonances. How can we describe that again? What's the analogy to think about with orbital resonances? Places where this might exist. Yeah, so in Jovian planets, we saw orbital resonances were important for the moons. Yeah, the moon's geologic activity of Io was produced by an orbital resonance with Europa, Ganymede, Callisto. Right? So they're all going around, and there's this like proportionality to their periods. So every time that Io goes around 4 times, Europa goes around twice, and Ganymede goes around once. Okay, so you'll notice there's these weird little fractions. What do the fractions mean? Well, here it says at this location, the object goes around once for every time that Jupiter goes around. Okay, at this location here, every time Jupiter goes around 3 times, Jupiter on the bottom, object on the top, this object goes around twice. Okay, over here. This one makes sense. This is 3, that's 12. If I divide those two, that's 4. Cool, good math. So here, if I go around once in 3 years, sorry, other way around. If I go around 4 times here in 3 years, that's 12, and Jupiter's only gone around once. So on the top is Jupiter, on the bottom is us, right? So every time that there are these weird integer multiples of one another, just 1 times 2, or 2 times 3, 5 times 2, we see these gaps. And that's because Jupiter is appearing at exactly the same location every time this asteroid gets back into the same part of its orbit. And so similar to when we push a friend on the swing, okay, if we give them just sort of random pushes, it doesn't go very far, right? It gets upset, kid starts crying. Okay, you push them at the end every single time, you can get a small push, eventually make them go all the way around. Right? That's the point of all swings, go all the way around. Okay. So think about going all the way around, but you're an asteroid. So you keep pushing, okay? Right here, push, 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 push. You give that asteroid enough energy, it's gone. Because I don't even want to be here anymore. And it pieces out. Okay? Question about this?
So the bottom is like every 4 rotations you make Jupiter, those aren't much spread, 1/4, right?
Yes, you make 4 rotations, so this times this gives you that number.
Okay.
Yeah, did I do it backwards? Yeah, this times that gives you that number. I might have done that. Yeah.
How do we extend our satellites past that?
Okay, good question. Very good question. So is this like a physical gap that we can't go by? The way to think about this, it's not a force field. Okay, this only happens if we are also in orbit. So if we're just passing through, it's not an issue. Okay, and in fact, we need to use Jupiter in a lot of cases to give us a little extra push to get out to the end of the solar system. But if we're trying to orbit for some reason, let's say we wanted to orbit in the asteroid belt, something we have to be very careful of. We cannot just sit here, especially for long periods of time. So if we go, let's say it takes 4 years to go around. Okay, we want it to sit here for 4 years. Okay, we're going to get pulled by Jupiter. It might only be a little bit. Okay, you have to use a little bit of fuel, make sure we stay in orbit, that's fine. If you wanted to stay there for millions of years, all of those little pushes would build up, and eventually it would get destabilized and thrown out of the solar system or into the sun. Usually it's into the sun. Okay, great question. Any other questions? Okay. So I made this analogy with Saturn's rings, but it's around the sun. They're not as pretty. Sorry. Saturn's rings are the coolest because they were recently destroyed icy moon. This stuff has been destroyed since it tried to form 4.5 billion years ago. Okay. Yeah, so this is another good example, and we'll probably talk about this more in detail. I'm just going to kind of put this here. I think a lot of you already identified this when we were talking about rings. You allow ring particles to exist. If you're not constantly creating them, what happens to them? Yeah, your rings disappear. Why would your rings disappear? Almost everyone has done this on the homework, so.
What dust that runs gets added when the dust, the composition of the form things, just added.
Right, yeah, so if we're thinking about, say, like Saturn's rings, stuff is continually being added. And so when that stuff leaves, where does it go? So for example, you have an object here, like Enceladus, which is adding the E-ring. Material from Enceladus is adding the E-ring. What's taking away from the E-ring? Yeah, so what is there already? It would be stuff that's like, let's say we're adding ice from Enceladus. Little pieces of ice come off, little grains, dust. What happens to that dust?
Comes back down, doesn't it?
Comes back down to. What is all of this orbiting? Saturn, right? So eventually, all of this stuff winds up probably in the center of whatever it's orbiting. In this case, the sun. I said you grind this stuff up, you move it around, you send an asteroid into the sun. Sun eats it up, no problem. Unless you're really, really small, like you make water, then water is a gas, it flies away, it's lost forever. Okay, so gas and dust do two different things, but we'll step in. Okay, so if you're not continuously replenishing all the dust in the solar system, the dust in the solar system disappears. Okay, and so this is a cool simulation. These are all of the objects. And before we do the lecture tutorial for today, I'm going to show you how they move. I hope this is a simulation, otherwise it's a really stupid picture. And it's to scale. There's some fun names here, the Trojans. The Greeks called them the Trojan asteroids. It's actually two of them. Died in that battle, and the Hildas. And all of this is our main belt. So you have your main belt asteroids. That's the white. Here's the Earth. What are all these things? Danger, right? All of that is dangerous. How did the dinosaurs die? Big ol' asteroid hit us. It sucked. Okay? All of this stuff, the reason why we care at all, we want to make sure that if we see it coming, we can do something about it. Okay, so this is why we track every single piece of dust, not dust, but every single piece of like basketball-sized material. Okay, because even if a basketball-sized asteroid hits the top of the atmosphere and it hits your house is gone. Okay, so hopefully this works. If it doesn't work, I'm gonna cry. Oh God. Oh damn it. Oh no. All right, let's do the lecture tutorial. I'll see if I can fix it in the meantime. So we're going to be learning today about Kepler's third law. And that's essentially thinking about, how do these orbits that we're talking about actually look? And are all of these, let me ask you a different question really quickly. Are these orbits all circular? No. Is it normal for all of the orbits in the solar system to be like Earth's? Most of the small stuff is elliptical. Recall what elliptical means? It's like a squished circle. So the very elliptical stuff that we're about to learn about, those are comets. The kind of elliptical stuff is asteroids. Okay. So break into groups of two. And if you don't mind distributing those around. If there isn't enough, let me know. Try not to grab one until everyone has one. Sorry, wait. Try not to grab one per in a group until everyone has. Okay. Okay. That's definitely not. That's FEMA. So that's like a what does FEMA stand for? Federal Emergency something agency? Yeah, EM.
Like, there'll be like a big, I think asteroid that hits, and then the government takes it, like, on the property.
So it depends on the country. If you find an asteroid, like there's so most of them have most of them are expensive, but that's just the collector's items, $10,000 per gram. It's great, right? You pick up a small asteroid, like great, you made a lot of money, but it's not very cool. There's like specific laws for finding.
Someone has made up.
No, so like, depending on.
Oh.
Civic law. Yeah, and some people just don't report it, they keep it forever, but then you also don't know what it is. So people will come and bring you the full iron slag, which is just like milk off from the refineries, and be like, this is dry, so then you go, and they'll be like, I tried this, put it in the NMR machine, oh my god. It's just metal, ground metal. Yeah. it's actually- Way up. And allow like sleep.
Yeah.
I'll take your.
Oh. Am I in here?
Well, the thing is, as I'm saying, like, I'm putting, whatever that was.
Which of the two ones? So this one further out. So this one can be. Motors can be created, stored. Yeah. Well, I thought. What they do is they move around the central store and increase the amount of time. You want to hold it. Remember, it's not hold the sassy. No, the difference. This one, I thought it really good. So it was fast.
Yeah.
But we have, it's like routine to turn around, right?
Yeah.
And earth rotation. So,
Right. So guys, you're right, that it does not depend on size.
There's a way of trying to put it, but you kind
Any of the things on
on the screen. My assumption.
You're actually.
That way. But that's more competitive. I think that's important. Yeah. But that's, yeah, what is about like this stuff.
So the reason why I was because we're talking about murder and it's that kind of thing in our solar system, there's nothing. Further away from the sun, so like those so we have another it's even smaller.
So do you think that this period is low?
That's what I would say.
It's all.
That picture. Drive home with comments, things that look like comment in the sky.
Yeah, exactly. Saw that going. Glowy.
Yeah, it's pretty cool.
Like.
I've seen it be what you do. You like these students to the way that you can always tell that they're lunches. Right, so like, all of they're just like from the end of the plane. It's actually quite small. Moving into the variation in the weight. See, this is so much more massive, but it's so much more powerful. Then it has huge impact on the wind structure.
Then I was thinking.
Does the mass of the object you're orbiting impact the period?
And they're never.
So object is more massive that you are orbiting, does it impact the period? Let's think about this one. If I'm the same distance away from the sun as I am from the earth, let's say I want to orbit both of them. Do I have the same orbital velocity for both of them? Which one have you on? Here's the earth. Here's the sun. And I have to orbit them. Here's the sun.
Yeah.
I'm taking a lot of time to think. Really going to be stronger at the same speed, right? So if I go the same speed that I go at Earth, that I go at the sun, that like so that I also don't think that's on one. It's but that running around is the speed. That's why if I do that same speed over here, same distance, but now this couple is not as strong, and just go.
Cause I'm like, what I'm like, speed.
Now, the opposite being not true. When we think about it, does my mass matter in that circumstance? Well, so when I travel this well, the earth rise up my ass is trying to find the earth, that's the earth, that's the earth. The difference is how much acceleration supports it. So another way to think about this, if I have the space station, you have all of the space station, and every single component in it has a different mass. And the orbital velocity, if it depended on the thing that was orbiting, then it would immediately come apart. Because every single mass would start orbiting at one speed. That is not what happens. Orbital velocity only depends on the thing that we are orbiting. Doesn't matter how big our mass is. And that's why when we look in the asteroid belt, we see massive things, we see small things. Right? That's why we see Jupiter more massive than Castor. Why we see Mars less massive in between these two objects. Right? So the object mass of the object orbiting does not depend, right, on its speed. Other way around. Okay. Was that okay? You want that explanation too? Yeah. So what I see here is like. So what part were you listening to? What part do you want to?
Yeah.
Depends on the mass. Funny stuff in the first, light stuff over the those will also be big, because when you're heavy stuff like big, the light stuff is bigger. You don't want that to happen. So back then, very well. That was so here's another one that I think was, okay? You have the so they're both on the same speed around the sun. What if the speed then go to the direction. The mass is still up there. Just not.
So it's been like, we're gonna have these questions or not.
Long as. We talked about this, I want to remember for this lectures, I think it's, like force of gravity.
Yeah.
Yeah, so notice this one says, early questions or sometimes. I'm not trading. The later question. They get into the end of the bot. So
If it's bigger, and it's different areas. Well, there are.
This is complete.
And then it's Flavian, and then you the hyper, and it's. But it's like dynamically eccentric, and these stuff would be good. Not coming all the way in.
So they're saying.
And you keep going out, it's all around the entire point. That's really good.
They're the same, but they never today. These are the same.
Yes. Hyperbolic object is not a. By definition, hyperbolic object, all in the same. Whereas a comet, by definition.
So.
So the object element is. All the way back. Highly. What's that? But never in a time. Let's just play the next slide. Let's see if we actually. All right, folks, we're gonna take a little break so we can do a little bit more content. Is that okay? Is that okay? 2 more minutes? Okay, 2 more minutes, fine. You're done? So for that one here, thinking about stuff going around the sun. Right? Same distance, the distance depend on. So they should be going at the same. Right, only by the orbital position, so the same orbital position, you have the same speed, how long does it take you to get all the way around? So notice this line here, early questions are sometimes easy as they seem, not always true. So there's really been an email that we have for- We'll grab this. There's a gravity. Yeah, with a little paragraph. I think it's describing this one. Not there. Okay, that's 2 minutes. Okay, we're starting. I thought this was a song for this. All right, so let's talk about this clicker question now that we have this all in our mind. So this picture on the right-hand side is a 2D image, and this is like a 1D image. We're gonna ask the question, why are there gaps in the top graph, but not in the cartoon below at the bottom? This is because A, the cartoon is drawn too small. If it were drawn larger, we could see the gaps. B, asteroid orbits are elliptical. Their location at a chosen moment, the cartoon, can occupy a resonance location, even if their average orbital distance is not. Graph. C, the cartoon shows a two-dimensional representation of a three-dimensional region of space. You can reread that. Let me know when you're ready to vote. First. Let's vote on 3, 2, 1. Okay, all right. All right. Anyone want to defend their answer here? Got a little bit from everyone. Anyone for 1? For 2? No one for nothing? Okay, let's think about this one through. Okay, so what did we just learn really briefly? Maybe haven't fully learned it. The Bush third law was talking about this relationship between the distance away you are from something and how long it takes you to go around, like this. Is that an accurate representation of where you'll be at every single moment? No, because I said that asteroid orbits are elliptical. Okay, so which one is it? B. Okay, good. All right, and this is a picture. I did find one of the simulations. These ones are cool. These are our Trojan asteroids. So everyone has a few Trojans. And here you see this is the sun. What's this one? Mercury. What's this one? I forget. I don't know which one is which. One of them's Venus. I think this is Venus, and I think that's Earth. And then that one is Mars. And we are actually going to shepherd these asteroids. So hopefully this works. Yes, let's go. So even though these individual locations, you're watching them go around. If I were to plot any one of those, would it be a perfect circle? No, not necessarily, right? So it might go in and out. And in fact, watch that red one. And you'll see that sometimes it gets a little closer and sometimes a little farther away. Okay. And that's why if we go back to this picture, now I'm gonna load this one. These ones are the coolest. Okay. So these ones too, they look like they're doing this triangle. They're not moving in a triangle, nothing moves in a triangle, but it looks like it in this still frame. And as they start to move around, you realize that they're all floating around with respect to Jupiter. So it's stuck in this picture. These ones here, they're all scared. This is I'm scared of Jupiter zone, right? Because it's gonna gobble me up. And then all of this stuff over here gets pushed by Jupiter. Okay. Okay. This one, just living free, living his best life. Actually, that turns out to be stable, just not a lot of things live there. Okay, so let's talk about this. So we talked about there are a large number of objects that are small, all of those little dots. And how much of the mass is in the 4 largest objects in the asteroid belt? 2/3? Okay, 2/3. Okay, so here's these 4 largest objects. They contain most of the matter. And all of these little ones contain the rest. And interestingly enough, that's a weird looking graph. Number of asteroids, 1. Lots of small asteroids. We're going to maybe tie that back to something a little later. Could that potentially be related to the impact crater? That could kind of make sense. Why does it have this shape? You know? This is a lab I want to make for next year. It's a really fun lab. I've done it before, but I haven't done it at this school. You take a brick, okay, and you hit it with a hammer. What happens? What? It breaks into how many bricks? Depends on how hard you hit it good, but usually more than 1. Okay, so if you break it, the hammer, you get more than 1 that are small. So if I took, say, a large object and I hit it with a hammer, I would get a lot of really small grains, some larger stuff. And it turns out that this sort of tells us what created the asteroid belt. The fact that this distribution is here, it's not from stuff sticking together. It's from starting from a big old thing and smashing it, not with a hammer, but being pulled apart by gravity by Jupiter. Okay? And then later on, they smush each other. And we see evidence of them smushing each other because we see impact crating all over the thing. Okay. Let's start really briefly talking about comets. That's a comet. Comets are really cool. This is a real picture, not an artist's interpretation. That's the sky. What's the first thing you notice about the comet? What's that? Tail? Has 2 tails. Yeah. So the quote about comets are like cats. They have tails and they do whatever they want. Sometimes they just decide not to work anymore. One of my first research opportunities was to look at a comet after it went past the sun. And after it went past the sun, it just decided to disintegrate. So I didn't get to study it at all. And then everyone gave me a card that said, sorry, your research burned out. So that was fun. Okay, so let's look at the different pieces here. There's this little nucleus that we're going to zoom in here. That's the center. That's where all the stuff comes from. A small dark chunk of ice. And if you look at this picture, it kind of looks different from the asteroids. It's small, 10 to 10 kilometers, much, much smaller than those round circular asteroids. Okay. There's a coma. This is just a fancy word for an atmosphere. It's this big gas around gas atmosphere here of basically gas and dust that's being liberated from the surface. You have a piece of ice, starts evaporating, and it puts gas and dust into space. Now, the atmosphere is not held on, just immediately escapes because the thing is small. Because it's small, doesn't have a very strong ability to hold on to any of the gas and dust. And so as it's driving, it's just littering, it's throwing out gas and dust as it drives. Okay? So there's the direction of motion. Comet's going this way. Oh shoot, wait, the dust and the plasma are going different directions. We'll talk about those. We have tails. These are pointing away from the direction of motion. Pointing away from the sun for the plasma, and sort of away from the direction of motion for the dust. We'll talk about why that happens. There's this plasma tail, that's the cool blue one. That's stuff that immediately gets ionized. So like electrons, ions, they get pulled away by the solar wind. That goes directly out. Okay. The dust tail is kind of weird, and we'll see more examples of this as we go on. All of this gas comes backwards here, and then immediately gets ionized and moves that way. The dust actually feels what's called radiation pressure. This is every single piece of light hitting it and slowing it down. And it starts to move behind the comet itself. That's why there's a curved piece to it. Here are some examples. This is the largest ones that we've visited by spacecraft. There's Happy, there's Wild. We'll talk about this one really briefly that we sent Rosetta to. 5 by 3 kilometers. Anyone have a good estimate how big that is? People really love kilometers. Okay. It looks like this. I'm going to show you a picture in a few seconds for scale. Does that look similar to what we saw before? What's majorly different about it? Yeah, there's like a chunk, or this chunk.
Yeah.
The chunk here. Okay. Okay. The texture? How's the texture look? Rocky? Okay, here's rocky. What about here? Right? I'm down to fall into that. This is like snow. This would be sick. You like go skiing, sick. You jump off that cliff, land in snow. Got very little gravity. You wouldn't really get hurt. Okay. We're not going to do this right now. Let me show you the size estimate in a few seconds. This is a different view of it. They flew all the way around it. They mapped the whole thing. It's beautiful. These are impact craters into the snowy ice mixture. They don't look as smooth. That's another indication that it's not an asteroid. Asteroids look more rocky because rock responds differently to impact cratering. This one, when you melt it, stays melty and then freezes, right? So it looks more smooth. And there's the good size comparison. That's LA, and so this would be like, okay, you do like a double black diamond. Sick, but okay, so let's leave you with that picture. Not imagine this hitting the Earth. And we'll talk about both comets and collisions on Thursday.
Quick question. The stuff that's coming off at the moment is it releasing from the center? That's why it's all